if you can hear me clearly. Okay. I want to welcome everyone to my lecture today. In fact, you are welcome to the new month of March, and you are also welcome to the new topic. Now, we actually want to start today. We call that random effects. And just like what I said on Monday, of course, attendance of lecture is very, very crucial to passing excellently in exam. So I will advise from time to time that you attend lectures. Okay, today, like I said, statistics is more or less like a story that goes on and on and on. Now, let me tell you the analysis of variance that we've been doing before now actually focus on fixed effects. Okay, today we actually, I'm going to introduce another version of that we call random effects. So in today's outline, I'm basically going to talk about, the difference between the fixed and the random effect. I'm going to show you the R example. So let's get started. Now, as you can see on the slide, we want to talk about the difference between the fixed and the random effect. You remember in this class the other time, we used an example under one-way analysis of variance, where we are actually comparing, we're looking at the effects of the type of sandwiches on attracting our hands. I remember, I think we focus on maybe 3 or 4 types of sandwiches. Now, in a situation where the levels of factors are kind of fixed, like for instance, we only have those types of sandwiches and nothing more, and we consider the effect of that in our research, we're basically going to call that a fixed effect. I'm going to say that again, looking at the example of the sandwiches that we considered the other time, we talk about the type of sandwiches, and let's say those are the only type of sandwiches that we have. There's no any other one. Okay, then we're basically going to refer to that as that factor as a fixed effect. But situation where we got more than, let's say for instance, we got more than 4 sandwiches, and we only select, maybe randomly, maybe we have like 20 types of sandwiches, and we only select 4. Okay, we're selecting 4 at random from the population of levels of an independent variable. That is no longer a fixed effect. That would be a random effect, because we also need to put into consideration the variance of the unknown population. So that is what I mean. Now, if you take a look at what I put on the board, I said up to now, we have only studied ANOVA model with fixed effect. So which means the one we've been working with, okay, we've been considering for fixed effect, whether we working with the one-way ANOVA, two-way ANOVA, three-way ANOVA, everything that we have done before today, I'm actually referring to them as fixed effect model. And that was why I said treatment effect are fixed when an investigator selects certain levels of factor to study. So their interest is about the performance of those levels only, where they're only focusing on those levels only and nothing more. and that will be fixed. But if there are more than those levels, and they only select at random few to study, then using a fixed effect model will be misleading, because another variability will be added to the total sources of variation. And that is the reason why in that kind of situation, we need a random effect instead of a fixed effect. Okay, and I think I gave enough definition here. I said a factor is random if its level consists of a random sample of levels from a population of possible levels. There's so many levels, you only select some levels to study. Because of that, that become a random effect. I'll give you another example. We've seen different countries, different companies coming out to say they have developed, a treatment, or they've developed vaccine, that actually work on COVID. I've heard about Pfizer, Moderna, AstraZeneca in Oxford, United Kingdom. I've also heard about Johnson & Johnson COVID vaccines. Of course, these companies actually claims efficacy. I remember Pfizer claimed 95% efficacy, Moderna about 95, and so on like that. Different vaccine company actually put out a figure out there. Now you're going to be wondering how they arrive at those figures. They arrive at those figures, maybe some of them they've used fixed effect model or even random effect model, or they've used a combination of the two. Now, I'm basically going to walk you through this example now, still on the COVID vaccine, if we really want to investigate how effective is a COVID vaccine. Of course, and we have selected some factors. If you want to test how effective is a COVID vaccine, it's like you want to figure out what is the probability of a vaccinated patient or of a vaccinated individual will not fall sick due to COVID. If I want to do that, we could have some factors like age. Okay, in the age, of course, we're going to have age bracket. Age is going to have levels, right? And then maybe I also have countries. Okay, when you take a look at country as a factor cannot be a fixed effect in that regard. You know why? Because COVID vaccine was not tested in all countries. I'm going to say that again. COVID vaccine was not tested in all countries in the world. They were only selected, they were only tested, the vaccine, the manufacturer of the COVID vaccine tested them, in some selected countries. And if you now want to take a country as a factor, of course, you're basically going to select countries out of, the countries where the COVID vaccine was tested, which means you are selecting levels out of levels. Don't forget, country is basically going to be a categorical factor because it has levels. If I have 10 countries, I got 10 levels. So because of that, we selected few. When we're doing that, then that country in that regard will be regarded as a random effect, not a fixed effect. Now, the only new thing that a random effect is going to bring in, okay, it's to enable us to incorporate variability due to selecting sample of countries. Because, imagine you want to conduct another experiment in the future, and you test it on countries that they've not tested that initially. There's possibility you could have a different result. And that is the difference between the random effect and a fixed effect. And we can also have a situation where we have the combination of the two. Like in the example I cited now, where I'm talking about COVID-19 vaccine efficacy. We can look at the effect of age. Age can be a fix. Age is going to be a fix when we consider all levels of age. Why countries is going to be random? Because the COVID vaccine was not tested in all countries. We're actually going to select few countries, the sample of countries from, where the COVID vaccine is actually tested. I'm going to give you another example because before I start showing you some, formula now, I think you need to first understand the reason why we are doing what we are doing. We don't just do what we do. We got reasons for doing that. I'm going to give you one example now, general example. I said, suppose you are interested in the natural degree of variation in sodium content across brand of beer. Okay. Sodium, you are interested in, sodium content. Okay. Across brands of beers. Okay. You're actually interested in natural degree of variation, natural degree of variations, natural degree of variation in sodium content across, brands of beer. But you know what? In the United States, there's so many brands of beers being sold. So many. And you only select 8 brands. Where do you get the 8 brands from? You get the 8 brands from the population of brands. And you're now trying to test whether, whether there's a different, you are testing this, of course, that, that's what you're testing here, whether in the 8 brands of, A, B, C, D, E, F, G, H, let me see, 1, 2, 3, 4, 5, 6, 7, 8. You are actually comparing the sodium content. But don't forget, these are not the only 8 brands in the United States. There are many. You only selected at random, this 8. Then here, of course, if this is going to be one way because I have a one factor, then this is going to be a random effect, not a fixed effect. Because in the end, you're basically going to make an inference, not only on this, but you're going to generalize on the entire brands in the United States. Does that make sense? That's what we mean. But in a situation where we only have 8 brands, and you test that 8 brands, then that's a fixed effect. You're already working with population, you're not working with sample, but this time around, you're working with a sample. I'm going to give you another example where we can have the combination of both fixed and random effects. For instance, you have 2-factor experiment. And I'm actually going to call two-way analysis of variance. Do you know that one factor could be fixed and the other factor could be random? In a situation where a factor is fixed, the other one is random. We call that a mixed effect. That's what I'm showing now. Mixed effect. Some factors are fixed, some are random. That's possible. And we could have a situation, the one we have done before, whether 2-way or 3-way, all factors are all fixed. When all factors are fixed, we call that fixed effect model. If all factors are random, we call that random effect model. But if a factor is fixed and the other one is random, we call that a mixed effect model. And I'm going to give you an example, real life example of a mixed effect model. If you want to talk about mixed effect model, of course, you're going to be talking about more than one factor, not just one. in a mixed, you have at least two factors where one is fixed, the other one is random. I'm going to give you an example. Suppose you are interested in the effect of a type of study program on student learning. Type of study program on students learning. Okay. I'm going to write that down. Give me 1 second. So type of study program. Okay. You are investigating type of study program, okay, on students learning, on student learning. And in addition to investigating the type of study program on student learning, you introduce a blocking effect. You remember on Monday, I walked you through introducing a blocking effect. Maybe the blocking effect you are introducing is school environment. School environment. That's another factor. School environment, right? Of course, looking at school, you have one factor here, and you also consider what I call a school environment. And you go to a large school district, and maybe basically you select just 4 schools. You selected 4 schools out of so many schools, right? Now, if you select 4 schools out of so many schools, then school cannot be a fixed effect. School is going to be a random effect. But the type of the program, maybe the type of the program you're talking about is computer and standard. Then the type of program here is going to be a fixed effect. You're only considering just 2 of that. There's no any other program you are interested in. Then the factor become a fixed effect. But the schools is a random effect because you are choosing 4 schools, okay, at random from the population of schools. And in each 4 school, you randomly select student volunteers. Maybe 10. Maybe you are using a balanced design, right? 10, 10, 10. And this 10, 10, 10, you randomly assign the 2 type of program to them. This is an example of a mix factor experiment. One factor is fixed, the other one is random. That becomes a mix. Okay, now I've walked you through so many examples on this now, and I basically want to walk you through model, because in statistics, if we want to provide practical if we want to provide a response or solution to practical problem, we're basically going to start with model. But we need to tell the world what kind of model are we going to use. Take a look at what I'm showing you now. Of course, if you take a look at the first one that I'm showing you is what we call a fixed effect model. That is for one-way ANOVA. Okay, where we only have one factor and that factor is fixed. Now, this is the way we specify that model. And of course, we have an assumption when that factor is fixed. Assumption is that the sum of the alpha I must be equal to 0. The sum of the alpha I equal to 0 because that's a fixed effect. And don't also forget, in every specification of a model, whether you're talking about 1-way, 2-way, 3-way, whatever way, we're always going to have what we call the error component. And let me tell you this, the error component is always random in every model. Now, in a one-way ANOVA model that I'm trying to show you now, why do I call it fixed effects? Whether I have a fixed effect, random effect, mixed effect, the error is always going to be random. Error in a model, will always going to be random. The name of the model, you can't derive the name of the model from the error. You derive the name of the model from the nature of the effects. If you take a look at what I'm trying to show you now, Yij equal to mu plus alpha I Eij. This is a one-way analysis of variance. And of course, we are assuming the effect of the alpha I is fixed. Even though the error is random, it is still called a fixed effect. And we expect the sum of the alpha I should be equal to 0. And that was why I said design a level of treatment are specifically choosing. You specifically choose them as if there is no any other levels that you are interested in. Therefore, you don't need any inference because you are already working with the entire, the entire levels you're interested in. And that was why I said statistical inference. What happened? Conclusion about the treatment effect apply only to the selected ones. At times, even though some people may argue this, even though you select some levels from the population, do you know you can treat that as a fix? But the only condition under which you are going to treat that as a fix is you are not ready to generalize on the one you did not choose. You only want to focus on the levels you are interested in. You are no longer interested in other levels. But if you choose level from a population of levels and you want to generalize, not only on the choosing levels, you want to generalize on the other levels in the population that you did not choose, of course, you need to go by random. That's what I mean. Okay, I want to show you another model now. And I need you to pay attention from what I'm presenting now. I'm seeing midterm 2. From what I'm presenting now, I'm seeing midterm 2. And that is the reason why I need you to be in class, to be able to get all the information. Now, I want to present a random effect model now for one-way analysis of variance. I just presented, if you take a look at this guy here, this is for one way for fixed effects. But this guy now, one way for random effect. What is the difference? Well, I wanted to focus. Oh my God, there's no difference in the model specification. But where do we have a difference? Where we have a difference is that initially our alpha high was fixed. The only thing that followed a distribution was the error. When a variable is random, it must follow a distribution. In the case of a fixed effect, our effect is fixed. Therefore, our effect will not follow any distribution because it's a fixed. But in the case of a random, in addition to the error term that follow normal distribution, then the alpha high will also follow normal distribution. Oh my God, it means the alpha high in the random effect will also have its own variance. But in the fixed effect, alpha high has a 0 variance. It doesn't have variance because it is fixed. Anything that is fixed is not subject to variation. But when anything that is random is subject to variation, now do you now see the difference between the two? Even though we specify the same model for one wave, for fixed effect, for random effect, but the difference is that, we got alpha high follow normal distribution with a mean of 0, sigma square alpha, and the EIJ follow normal distribution, with a mean 0, sigma square. So what's the difference between the fixed effect and the random effect here is just like, okay, in the fixed effect, the treatment effect does not follow any distribution. But in the random effect, the treatment effect follow normal distribution. And when it follow normal distribution, it means the mean of that and the variance of that exists. And let me tell you, in the fixed effect model, the summation of the alpha high was equal to 0, but in the random, that would no longer apply. Like I said, I'm seeing a lot of questions here from midterm 2. What of if they ask you to differentiate between one-way analysis of variance for fixed effects and for random effects? This is the description now. This is the how to distinguish. And when we come to the design, the level of the treatment are randomly choosing for random. That's why it's called random effects. The levels are randomly choosing. What about the statistical inference? Of course, we conduct a statistical inference. It means conclusion about the treatment effect apply to all levels of the treatment in the population, even though we've only selected some few levels of the treatment, but in the end, we're basically going to generalize. Statistical inference means generalization. Okay, what are you generalizing? You are generalizing the results of the sample on the entire population. That's exactly what we mean. Now, I want you to see, do you know that when we're working with a random effect model, we need to derive a variance. The variance of the Yij, which is the response, for fixed effect is different from the random effect. For random effect, okay, that will be additional variance that we call mean. Oh my God. What is the variance when if you want to talk about a fixed effect model? The variance of the response is sigma squared. But when you want to talk about random effect model, oh my God, another variance is coming in, which means we are introducing another variability. And this time around, the variability of the treatment effects. And that's why you see sigma square alpha, which means the variance of Yij. If Yij is a response in a random effect model, the variance of Yij is basically going to be sigma square plus sigma square alpha. But this variance, the sigma square alpha does not exist when you talk about fixed effect model. But now it exists when you talk about random effect model. And let me tell you, because of that, we're basically going to talk about covariance. Because we actually realize in the fixed effect model, observation within any group should be independent. You know that? One of the assumptions, right? In the fixed effect model. But that assumption will be violated here because we expect some form of correlations. And that is the reason why we need covariance. Since we already have a variance, this is a total variance, right? We also need covariance. Then the covariance here is just going to be sigma square alpha. And don't forget, correlation is the ratio of the covariance to the product of the two standard deviation. Look at what I have now. The correlation between Yij and Yij or prime. I'm talking about observation within a group. The observations within the group in a fixed effect model, they are actually going to be independent. When they are independent, the covariance equal to 0. When the covariance equal to 0, correlation equal to 0, it means they are unrelated. But in the case of a random effect, they are not. In the case of random effect, they are not independent. They are not independent means they correlate. And when they correlate, then we'll be able to obtain the covariance. Not only that, when we have the covariance, then we also will be able to obtain the correlation. And what is the covariance here? The covariance is going to be the sigma square alpha, the variance of the treatment effect. That would be the covariance. And what will now be the correlation? Oh my God, the correlation is going to be the ratio of the covariance to the totality of the variance. What was the totality of the variance in the model? Sigma square alpha plus the sigma squared. What did the sigma square represent? The sigma square represent that is the variance of the error. In any statistical model, there's always going to be the variance of the error. There's always going to be error. And that's why you have what I'm showing you now is what we call the correlation. So which means in random effect, we actually compute correlation. And which means before you can compute correlation, you need the sigma square alpha and the sigma square. Now, we are actually call that correlation, we call it intra-class correlation. Oh my God, intra-class means within the same group. But don't forget, in the fixed effect, they should be independent, but in the random, they are not. If they are not independent, then correlation exists. Okay, so what I'm trying to show you here, some could have a high correlation and some could have low within different groups. Okay, now when we're talking about random effect model, we normally emphasize more on the variances because the random effect model actually incorporates, okay, new variability. So we're going to focus more on the variances. And another thing I wanted to know, the variance components that we talk about, they are not the same as the mean square error in a normal ANOVA. I wanted to take note of that. And of course, you know, when you're talking about random effect model, we could have a one-way, two-way, three-way, and so on like that, just like what we have in the fixed effect or conventional fixed effect model. So the typical inference will be point estimate or confidence level for the variance component or a test of the null hypothesis that the treatment variance sigma square equal to 0. Oh my God, what are we actually testing in the fixed effect model? What we are testing in the fixed effect model is to test whether alpha j equal to 0. But in the random effect model, we are not focusing on that. We're focusing on the variance. Variance of what? The variance of the treatment effect. Take a look at that. Okay. And that was why I say in this model, the treatment effect, alpha high, they are random variables. I think you know that. Okay. Not parameter like in the fixed one that you've done. So therefore, we are not interested in making inference about alphas. Okay. But what we are interested now is the variability. Now I'm going to show you the summary, you know, of one way ANOVA. Take a look at what I'm trying to show you on the board now. What is the summary? What does it take away? When I have a one way ANOVA, that's a fixed effect. Okay, how does the model look like? When I have a one way ANOVA, that's a random effect, how does the model look like? Oh my God. If you take a look at the fixed effect, the response variable, we follow normal distribution. What would be the mean? The mean is just going to be mu plus alpha. We're talking about response now, the response variable. And the variance will be sigma squared. That will be for fixed effects. And which means the variance of the error will be the same as the variance of the response when you're talking about fixed effects. I'm going to say that again. The variance of the error is sigma squared. You all know that in the fixed effect model, the variance of the response is also sigma squared. Because in the fixed effect, we don't talk about the variance of the treatment effects. The variance of the treatment effect is going to be equal to 0 because in the fixed effect model, the levels are not random. They are fixed. Therefore, the variance should be 0. But when you talk about the random effects, actually going to have not only the variance of the error, we're also going to have the variance of the treatment effect. And that's why you see the Yij equal to mu, comma, sigma square alpha plus sigma square. Let us compare the two response variable in both one is both fixed effect and the random effect. Their mean is not the same. Their variance is not the same. I need you to focus more on what I'm presenting now. What of in a situation where you are asked to differentiate between the response in fixed effect model and in a random effect model. Look at that. Even though Yij follow normal distribution, the mean is not the same. In the fixed effect, the mean is mu plus alpha high. But in the random effect, the mean is mu. Look at that. Then what about the variance? In the fixed effect, the variance is sigma squared. But in the random effect, the variance is sigma squared alpha plus sigma squared. Take a look at that. In the fixed effect, observations are all independent. In the random effect, not all observations are independent, and that is the reason why we're calculating covariance. That is the reason why we're calculating interclass correlation. Now, I think I've just talked about all that. I'm basically going to move. I've told you, I've shown you the reason why we actually use the random. Now, take a look at it. Why use random effect model when you randomly select treatment from a population? If you don't randomly select treatment, when I say treatment, of course, factor, levels of factors. Does that make sense, right? Okay. Now, treatment are supposed to represent a population of interest about which we wish to learn. So we have a population of that. And of course, we wish to understand the variability of the population. Anytime you are randomly selecting your treatment, then it means you need to understand the variability of the population as well. Okay. And we need to control for that. Now I'm going to walk you through an example. Now take a look at this example. What you're going to be seeing in this slide now, we could ask you some questions. We could give you some practical scenario and ask you to identify what would be the appropriate model. Are we going to use fixed effects or are we going to use a random effect? But right now, I think I've just explained to you what is the meaning? What is the difference between a fixed effect model, a random effect model? The moment you randomly select levels of treatments from a population, that automatically become a random effect. But if you don't randomly select them, and maybe you only have those levels in the population, and you focus on all of that, or you are interested in a particular one, and you are not interested in making inference, we're not interested in generalizing them on the entire level, so you did not select, of course, you can go for fix. Now take a look at it. Or consider a study of a battery life measured in hours, where 4 brands of batteries are evaluated using 4 replication in a completely randomized design. When you take a look at this, the question now, should the brand of battery be considered a fix or random? That is up to investigator. That's up to investigator. If there are so many brands and the investigator only choose 4 out of so many brands, then that would be random. But if this is the only brands that are available in your company, then you go for fixed effect. Any question? Any question on that? Okay. Now, I think there are other questions as well. I think I answered that here. Okay. This is another question. In fact, I'm going to give you an example now. Let's say in a clinic, we have 5 doctors, only 5 doctors in a clinic. And we basically want to see whether patient satisfaction varies across those 5 doctors. Then what are we going to use? That would be a random effect. Oh, sorry, that would be fixed effect. Because you know why? Fixed effect. Because we only have 5 doctors and we're using all of them. But what if we have more than 5 doctors and we're only selecting 5? Okay. Then it means in the end, selecting 5 doctors, whatever result you get, you generalize on the entire population of doctors, then that qualify to be a random effect. I think I asked a lot of examples, but let me quickly show you the model, the ANOVA table. Oh my God, the ANOVA, the way we write the ANOVA table for a fixed effect model is different from that of a random effect. Of course, you're already familiar with the way we present ANOVA table for fixed effect. But the only difference in the ANOVA table for random effect is that we're only going to we're going to have a section that we're going to call expected mean squared, which is going to be called EMS. Of course, the degree of freedom still remains the same. Like Joe, G minus 1. If I have numbers of group is G, then the degree of freedom is going to be G minus 1. The degree of freedom for error is going to be M minus G. But you know what? In the random effect model, we consider expected mean squared. Now, the expected mean squared for the treatment now is going to be sigma squared plus N sigma squared alpha. But for the error, it's going to be sigma squared. Take a look at that. Okay. Now, and do you know that the EMS is the expected mean squared that I said, and of course the EMS for the error is sigma squared. And do you know we can ask you to find sigma square alpha? What is sigma square alpha? That is the variance of the treatment effect. Don't forget, that is sigma square alpha. You can be asked to find that. Okay, I'm going to walk you through now how to do that in R. Take a look at this now. We actually, if you want to do that in R, you want to conduct a random effect in R, you basically need to load a package called LME4 in R. Take a look at that. Okay, now you want to estimate batch to batch variability in a chemical process that affects the yield of dye stuff, batch to batch, right? And we realize that there's so many batches, of course. We want to talk about batch to batch variability now. And of course, in the experiment, 6 batches of an intermediate product, H acid, were made, and 5 preparations of this product were made in the laboratory for each batch. That's a balance, right? Okay, now this is the code. Now let's look at the ANOVA table. You're still going to have the regular code, the same one that you have when you were considering the fixed effect model. But there's going to be additional information. Oh my God, what is the additional information? We basically want to find the sigma square alpha, because the sigma square alpha is not going to be captured as part of the arrow output. Take a look at what you have now. Even though it's telling us here, oh, there's a significant difference in the batch. We're not only interested in that. We also want to obtain the sigma square alpha. And how can we obtain the sigma square alpha? Don't forget the other time in the EMS column here for treatment, it is sigma squared plus N sigma square alpha. And I need to solve an equation. I'm actually going to equate that to what? I'm actually going to equate that to 11272. What is 11272? That is the mean square for treatment. If you look at that ANOVA table, the 11272 is actually the mean square treatment for, that is a mean square batch. That is a mean square treatment. And don't forget, in a random effect, the sigma squared plus N sigma square alpha must be equal to that. Now, what are we looking for? We're looking for sigma square alpha. But what is sigma square? Okay, sigma square will be mean square error. Where is the mean square error coming from? Go to the ANOVA table, 2451. Do you see the mean square error? Then you're going to plug that in. Then you're going to solve for sigma square alpha. Oh my God. What is my sigma square alpha now? Solving for that, I got 1764.2. From there, I can get the standard deviation, which is going to be the square root of that. Take a look at that. And the moment I got this guy, I can also find the inter-class correlation. Okay, so take a look at that. This guy is just the plots. When you look at the yield, when you plot the yield against batch, of course, this is the box plot of that. I think I still have like 5 more minutes. Now, let's come to the remarks. Before coming to the remarks, of course, what I'm just going to say here is just like what some scientists or statisticians have said about, random and, and the fixed effect. But I'm going to quickly move now to another example. Take a look at this example, right? We've actually got our ANOVA table, right? Okay, and from the ANOVA table, we need what? The sigma square alpha, right? And we solve for that, just like what we did. But we could have a situation where the sigma square alpha is negative. When it is negative, we cannot use the method we're using anymore because the variance can be negative. And let me tell you, in the fixed effect model, we use a least square method and the method of maximum likelihood. In the random effect model, we use a shrinkage method. We use a shrinkage method, but situation whereby if the sigma square alpha is negative, then we need a new approach, which I'm going to discuss in the next class. Okay, we need a new approach because your sigma square, the moment your sigma square alpha is negative, it means you can't find your sigma. You can't find the standard deviation. The square root of a negative does not exist. Therefore, we need a new brand approach for the random effect, okay, which we're going to do in the next class. Now, lastly, before I go, I've discussed today the one-way random effect, right? What about two-way? How does it look like? The two-way random, oh my God, the two-way random effect. Factor A is random. Factor B is random. How many variances that are coming to join the conventional sigma square? There will be two variances. Look at your table now. Look at the ANOVA table. Okay, for the random effect. If A is random, we're going to have a sigma square plus sigma square alpha beta plus MB sigma square alpha. Of course, I'm actually going to allow you to, with a two-sheet sheet in exam, this may be part of what you're going to write down, because for treatment for factor A, that is expected mean square. For factor B, that's expected mean square. For interaction, that's expected mean square. Error remains sigma squared. Now, this is for two-way ANOVA now, where A is random, factor A is random, factor B is random, factor A and the interaction is also random. Of course, when the factor A is random, B is random, of course, their interaction will also be random. Okay, and what is going to be the expected MS? If you take a look at factor A, okay, what are you seeing? You're seeing sigma square interaction plus sigma square alpha. In the expected mean square for factor A, you will not see sigma square B, but you're only going to see the sigma square of that factor and the interaction. But in the case of the interaction, you're only going to see the variance associated with the interaction only. How do I now test for F? Don't forget, when you have a two-way ANOVA, I'm going to test for factor A, factor B, and factor AB. But the way we test that in random effect is different from fixed effect. That of fixed effect is straightforward, but the random is not. Now, hypothesis number one is talking about interaction. You know what it's doing? It's trying to say EMS in the interaction divided by the sigma squared. Do you see the F now? The EMS in the interaction divided by the sigma squared. If I want to test the effect of, and what am I testing? We're no longer testing means, we're testing variances in the random effect, because the effects are no longer fixed, effects are random. Look at that, and look at the last one. You can see the ratio of what? The ratio of the expected mean square divided by that. Take a look at that. That's what you see. That's what we're testing. What is next? New approach. Situation where sigma square alpha is negative. What is the way forward? Then I'm going to walk you through more example in the next class. Any question before I go today? Any question? Do you really enjoy today's class? If you're enjoying today's class, okay, this is what I need you to do. Send me a message. Rate your understanding of today's class from 0 to 100. If it is less than 100, tell me what I need to clarify. Does that make sense? Because we are starting a countdown to midterm 2. You know what I'm going to do? The area covered in midterm 1 will never be in midterm 2. The midterm 2 starts from two-way ANOVA. Does that make sense? The midterm 2 starts from two-way ANOVA, which means one-way ANOVA will never be tested in midterm two. Make sure you stay safe. See you on Friday. Oh, wait, I think I have a chat, a message. Oh, you just say yes. Okay, make sure you stay safe. Have a very beautiful day. Bye for now, everyone.